In this video, I will talk about mathematical description of simple pendulum motion, and the setup is the following. So that's a string with length L, and a mass m is attached to the string. The string is then pulled to an angle theta, and then let go. Okay. So the resulting motion is that this mass m is going to oscillate back and forth along this equilibrium position. So the vertical line here is equilibrium position. Okay, so first let's draw a free body diagram for the mass m. There's a tension force T acting on the mass m and point along this string direction. There's also gravity mg. Okay. So to write out Newton's second law for this mass m's motion, we need to decompose the force into a direction pointing to the center. So the center here refers to the other end of the string, and because this mass m is doing part of the circular motion, so O is the center of that circular motion. Okay. Now let's define direction along the string direction. We define it as radial direction, which is r hat. R hat is unit vector along radial direction. And perpendicular to the radial direction is the tangential direction. And we use a unit vector t hat to represent it. Now let's write down Newton's second law for these two directions. Along the radial direction, the object m is doing circular motion. So the net force along radial direction is given by tension T and mass mg's radial direction component. Okay, so this angle is also theta. It's the same as this angle. And mg's component along this direction is mg cosine theta. But there should be a negative sign here because it's opposite to the radial direction. Okay, so that equals ma radial direction, radial acceleration. And along the net force along the tangential direction is given by negative mg sine theta. That's this component. That's the mg sine theta component. Okay, and the reason we have a negative sign here is because the force component is opposite to the tangential direction. And we define this tangential direction as positive because this direction is along the direction that increases theta's value. So if theta increases along this counterclockwise direction, we say that direction is positive. Okay, so now mg sine theta is opposite to that, so that's why it has negative sign. And that equals ma tangential. Now we're going to focus on the second equation, this one here, to describe the simple harmonic motion derived from the simple pendulum system. Okay. So to do that, let's rewrite this at as, because this one, the circular motion here has radius L. Okay, so equals L times alpha. Alpha is the angular acceleration. And alpha equals the second derivative of angle theta with respect to time. Okay, so now let's rewrite the second equation as negative mg sine theta equals m times L, second derivative of the angle theta with respect to time. And we're not yet arriving at the standard differential equation for simple harmonic motion because we have sine theta here instead of theta. So let's do one approximation here for small theta angle. Sine theta is equal to theta. Okay, so that can be satisfied when we set up the oscillation here. So let's say we pull it to a small angle, and this angle is less than 10 degree. Okay, usually less than 10 degree, then we have this condition here. Okay, so now we have, under such an approximation, we have negative mg theta equals ml, second derivative of theta with respect to time. Okay, so that can be written as the standard form d theta dt squared plus g over L times theta equals 0. So that's the standard form of simple harmonic motion. And its solution is theta equals theta naught, which is the initial angle that we pull the string, okay, to this initial angle, which is also the amplitude of the simple harmonic motion. So theta naught times cosine omega t plus phi naught. Again, omega equals square root g over L. And this angle, because that's the initial angle of the string, so this angle is actually also theta naught. Okay, and that's also theta naught. The initial angle less than 10 degree. Okay.